In this video, I'm going to discuss about the structure of benzene aromatic from the chapter aromatic hydrocarbons in detail. Yes, when we look at how this aromatic compounds got its name, first of all, early in the history of organic chemistry, yes, so chemists actually discovered a few compounds which were having high stability. That means they're unusually stable and they have some distinct odor. Actually, aroma means in Greek, aroma means fragrance smell, right? So fragrant smell. So actually, when the chemists discovered this, the compounds which are having this distinct odor, that means the fragrance smell, and they were unusually stable, they call them as aromatic compounds because aroma means fragrance smell in Greek. Yes. And then, but today, when we look at it, these compounds the term aromatic has been used irrespective of the odor. So most of the aromatic compounds, now we are calling them as aromatic compounds, are little odor or no odor at all. So actually, the word aromatic is used in a different sense here now. But earlier, because the class of the compounds which were unusually stable and having the fragrance smell or the distinct odor were called as aromatic compounds. So what is the first point here? They were unusually stable and with the pleasant odor or aroma, and because of the presence of the high percentage of carbon in them, here is the third point. They were found to be having the high percentage of carbon content in them. Right. And what is the chemical reactions or the chemical behavior of these aromatic compounds were very quite different from those of aliphatic compounds. So when we sum up this, so they were unusually stable and they're having the pleasant odor and they have the high percentage of carbon content when compared with the hydrogen, and their behavior was also quite different from that of aliphatic compounds. Yes, so they can be again obtained from natural sources like benzaldehyde was obtained benzaldehyde can be obtained from cherries, natural sources, peaches and almonds, for example. So actually, benzene is a classic example of these aromatic compounds. And when we look at these physical properties of benzene, it was isolated by Michael Faraday in 1825. It is a colorless compound and it is a liquid. Right. So when we look at the melting point of this, it is 5.5 degrees and it's a boiling point of 80 degrees centigrade. Right. So when we look at the miscibility in water, again, it's not miscible in water and it's soluble in organic solvents. And yes, it is has an aromatic odor. Right. But here, today the benzene, yes, as we know the structure of benzene, it looks very simple when compared to that of this highly complex structures, but it took more than 100 years for the scientists to evolve at the correct structure of this benzene, because of not because of its complexity, but because of the limitations of the structural theory developed at that time. So it took more than 100 years to evolve the correct structure of benzene. Yes. So when we look at the structure of benzene here, how they evolved at the structure of the benzene, we know from this molecular weight determinations and elemental analysis, the molecular formula of benzene was given to be C6H6. So with the molecular formula of C6H6 here, so here's the structures which were consistent with the C6H6 molecular formula were proposed. So the 5 structures which were proposed are CH3. Yeah. So these are actually the structures which were proposed for C6H6. So this will be triple bond, I'm sorry. It again. Yes. So CH3, C, triple bond C, C, triple bond C and CH3. 6 carbon atoms here. So this is a structure 1 which was proposed. And what is the structure 2? Structure 2 is also with, it should be fit into this formula of C6H6. So CH2, double bond, CH, C, triple bond, C, CH, CH3. This is the second structure which was proposed. And we look at the third structure. It is a cyclic structure with 5-membered ring and 2 double bonds. This is the third structure which was proposed for benzene. And the fourth structure is the structure which was proposed by Dewar. So Dewar structure we call it as. So this is the Dewar structure. And the fifth structure is of the Kekulé structure, right? With alternating single and double bonds. This is a fixed structure which we call as Kekulé structure, right? So these are the 5 structures which were proposed then, which, based on the elemental analysis and molecular weight determinations, it was found that the molecular formula of benzene is C6H6, and based on this molecular formula, it consistent with this formula, 5 structures have been proposed, right? So here, when we carry out the few reactions like chlorination, bromination and nitration. So bromination and nitration, here we observe that it is giving only single product. That means it is giving only mono-substituted product. So all these were giving what? Only mono-substitute. When the benzene was subjected to this chlorination, bromination and nitration reactions, what is observed here? We are getting the mono-substituted product. What does it mean? So if you're getting the mono-substituted product, it means that all the hydrogen should be equivalent. Right? It means that all the hydrogen should be equivalent. So in which the structures, all the structures are, all the hydrogens are equivalent. Yeah, this structure where the carbon number 1 and carbon number 6 are, same type of hydrogen. So the hydrogens in this first structure are equivalent. And again, this one, no. So this is of one type hydrogens, this is another, this is primary and this is secondary. So there are no other hydrogens. If you look at it, there are more, many more hydrogen types here. So one type and these are all other type. So Dewar structure also not one type, so more than one type. So more than mono-substituted product should be formed if the benzene structure was formed. Here again, if you take this one, the hydrogens which are present on this are all of one type here. So if there are one type of hydrogen, so only one mono-substituted, mono-substituted product will be formed. So here 3 structures will be ruled out. That is structure number 2 can be ruled out, 3 can be ruled out, and 4 can be ruled out. Only structure number 1 and structure number 5 are taken into consideration because on chlorination, bromination, and nitration of benzene, we are getting what? Only one mono-substituted product, which means that there should be only one type of, which indicating that all the hydrogens in the benzene ring are equivalent. And only in structure number 1 and structure number 5, all the hydrogens are equivalent, so all the other 3 structures are ruled out. Right. Here again, now we have, yes, we have 2 structures, that is 1 and 5 again. And again, it is said that benzene, yes, benzene again forms 3 isomeric di-substituted products. So we have one of the Kekulé structure and the other one is where the open chain structure with all, the hydrogens are equivalent here, right? These 2 structures, when di-substitution product, when we are looking at the di-substituted product of this, we see that we are getting 3 isomeric di-substituted products. Yes, 3 isomeric disubstituted products. So when we look at this open chain structure of, if this was the structure of the benzene, that is the open chain structure, we can get only one disubstituted product, and there is no isomers which are possible for this, right? So there is no isomers which can be possible for this, only one disubstituted product can be formed. But if we are taking the structure of the benzene to be closed chain structure, that is Kekule structure, we can say that the 3 disubstituted product here is 1 at 1, 2 positions, 1, 3 positions, and at 1, 4 positions. So 1, 2, 1, 3, and 1, 4 disubstituted products can be formed, and these are isomers. So why are we calling this as isomers? They have the same molecular formula, but they're differing only in the position of this functional group. Only the position of the substituents is differing here, so we're calling it as isomers here, right? So if the structure were to be open chain structure, we are taking this to be 1, we should get only 1 disubstituted product, and there is no isomers which are possible. But the isomers can be possible only when we are taking the Kekule structure, that is structure number 5, and the 3 isomeric structures are as shown below, that is 1, 2 disubstituted, 1, 3 disubstituted, and 1, 4 disubstituted. And finally, the Kekule structure was the correct structure for benzene, where it is having alternating single and double bonds. Yes. And again, when we take the Kekule structure here, if you take the disubstituted product here, if I take the disubstituted product here, right? Yes, if I take the disubstituted product here, again, in the 2 disubstituted product, that is 1, 2 disubstituted benzene, here again 2 isomers should be possible, right, which are differing in the position of the functional group, right? If I'm taking as 1, 2, 3, 4, 5, and 6, here between 1 and 2 there is a double bond, here in between 1 and 2 there is no double bond. So this is differing only in the position of the double bond. But in practice, when you observe, only one disubstituted product is possible. So in practice, what is there? Only 1, 1, 2 disubstituted benzene is possible. What does this mean? So only 1 disubstituted benzene is possible here. Substituted benzene is possible here. So what does this mean here? Yes, if only 1 disubstituted product, that is 1, 2 disubstituted product is possible, which means that here can be explained. So this can be explained by the concept of resonance here. So the concept as resonance has been introduced in order to explain why only 1, 2 disubstituted product can be, or 1, 2 disubstituted benzene exists. So the concept of, the concept of this can be explained when we take resonance into consideration, which means that to support the fact that only 1, 2 disubstituted benzene exists, concept of resonance has been introduced, where in resonance there it states that the double bonds here are in conjugation. That means they can shift their position in between these double bonds here. That is why the double bonds do not belong to any carbon atom here. They belong to all the 6 carbon atoms as a whole. The 3 pi bonds here, or the 3 double bonds, belong to all the 6 carbon atoms, or they share all the 6 electrons. 6 carbon atoms share 6 electrons. So this is represented by means of a resonance hybrid, which is shown below, where it shows that the electrons do not belong to any 2 carbon atoms here. They belong to all the 6 carbon atoms, where the concept of resonance has been introduced here. So yes, so this is about the why only 1, 1, 2 disubstituted benzene exists, right? So again, when we look at the stability of benzene, yes, it is unusually stable. It is unusually stable. So even though it has 3 double bonds, so how many double bonds? It has 3 double bonds. So it's similar to that of an alkene, right? So since there are 3 double bonds here, we can we can actually compare with an alkene here. So if it was behaving like an alkene, so it should undergo addition reactions. So what type of reactions it should undergo? Addition reactions it undergoes. It should undergo addition reactions. Right, but it is not undergoing addition reaction. Instead, it is undergoing substitution reaction. So what is the characteristics of this aromatic compounds is the main thing is it undergoes substitution reactions instead of addition reactions. Right. So if it were to behave like an alkene, it should undergo oxidation, but it is not. It should decolorize bromine water. That means it should react with bromine, since alkanes react with bromine, undergoes the addition reactions resulting in the formation of dibromo alkane here. So, but here it does not decolorize bromine water. So it does not decolorize bromine water, which means that it is not behaving like alkenes. It is not undergoing the characteristic reactions that alkenes undergo. It is undergoing substitution reactions. It is resistant to oxidation. It is not decolorizing bromine water. Unlike alkenes, and also they're unusually stable, even though it has 3 double bonds as given by Kekulé structure. Right. So when we take the heats of hydrogenation values, yes, what is heat of hydrogenation? Heat of hydrogenation actually is the amount of energy evolved when 1 mole of this unsaturated compound is hydrogenated. So 1 mole of this is hydrogenated. Is amount of heat evolved when 1 mole of this is hydrogenated. Yes. So for alkene, for 1 double bond, the heat of hydrogenation is given to be, actually it is expected to be 28.6 kilocalories per mole. When 1 mole of this, so what is heat of hydrogenation? It is the amount of energy evolved when 1 mole of this unsaturated compound is hydrogenated. So for 1 mole of double bond, that is, for example, if a cyclohexene, that is, it is consisting of 1 double bond, is hydrogenated, the amount of heat evolved is 28.6 kilocalories. And if the cyclohexadiene, if this is hydrogenated, that means it is having 2 double bonds, the heat of hydrogenation, the amount of heat evolved is 55.4 kilocalories. So in this way, if you think of it, this benzene to be cyclohexatriene, this is what cyclohexane. This is cyclohexadiene, and this is cyclohexatriene, benzene. So when cyclohexane was hydrogenated, the amount of heat evolved is 28.6. Heat of hydrogenation is 28.6 kilocalories per mole. For diene, it is 55.4. For triene, the expected value will be 3 into 28.6. It should be 85.8 kilocalories per mole. Right? So if it were to undergo if it were to evolve the heat in the same way as a diene or the single double bond, it should produce 85.8 kilocalories of mole per mole the heat. That is heat of hydrogenation. But unusually, it is experimentally, it has been it measured that the heat of hydrogenation is only how much? So unlike this one, it was 49.8 kilocalories per mole. So what is the difference in between these two? This is 36 kilocalories per mole. So in other words, so lesser amount of heat is evolved when cyclohexatriene or benzene is hydrogenated. But the actual value is how much? Only 49.8. Expected value is 85.8. That is 3 into 1 double bond, 28.6. But only 49 kilocalories of heat is evolved. So, well, difference being 36 kilocalories per mole. So we can say this difference as, that means this is a expected value, this is the actual value, the difference is 36 kilocalories per mole. We can say that 36 kilocalories of per mole heat is evolved less when compared to that of the actual value, or benzene is more stable than expected by 36 kilocalories per mole. And this 36 kilocalories per mole is called as resonance energy. So we already said this is unusually stable. And why it is unusually stable? Because the heat of hydrogenation value of this is less when compared to that of this expected value. It is less by 36 kilocalories per mole, and we are calling this as difference as resonance energy. So in other words, we can say that the benzene is more stable by 36 kilocalories per mole. So when we look at the bond length of this, so how many double bonds are there here? 3 double bonds and 3 single bonds. So what type of bonds we can see here? Single bonds and double bonds. So CC length, single bond length is 1.54 angstroms, and double bond length is 1.34. So what are the expected bond lengths in benzene? It should have 1.54 angstroms bond length, and there should be 2 types of bond lengths of 1.54 and 1.34. But here we can say that all the bond lengths are of the same length, all the bonds are of the same length, and it is to be 1.39 angstroms, and somewhere in between the single bond and the double bond length. The single bond and the double bond length here. So here, what can we say again? The concept of resonance here. See, so the double bonds which are present here is not belonging to any 2 carbon atoms. They are in conjugation, or they are in resonance here. So the real structure of benzene cannot be represented by any one of these Kekulé structures at one single time, but it can be represented only by means of this resonance hybrid, where all the 6 electrons are in resonance. They are moving in between these carbon atoms. So this is a resonance structure, which is actual structure of benzene, and it cannot be represented by any one of these Kekulé structures at any any given time. Right. So when we look at the orbital picture of benzene here, so now finally we got the structure of the benzene, where we have the 6 carbon atoms arranged in cyclic manner with the alternating single and double bonds here, and each of these carbon atoms is attached to one single hydrogen. Right. So this is a planar molecule, right? So here each carbon atom is linked to 3 other atoms by means of sigma bonds here. Right, so there are 3 sigma bonds, and each carbon atom we can say that it is sp2 hybridized. So carbon, we know that atomic number is 6, so 1s2, 2s2, 2p2. Right, so in the excited state, it will be in the excited state, so it will be, so one of the electrons of this is excited to the p orbital. So this is excited state configuration, where it undergoes sp2 hybridized, 1 s orbital and 2 p orbitals undergo the hybridization, resulting in the formation of 3 sp2 hybrid orbitals. On each carbon atom, they will form 3 sigma bonds with 2 other carbon atoms and 1 hydrogen atom. So there is a single unhybridized p orbital which is left here on each of the carbon atoms here, and this single unhybridized orbital you can see here on each of the carbon atoms here, and the electrons from this here, the p orbitals of adjacent atoms overlap. So they overlap here, so we can see the overlap here. So overlap and form 2 continuous donut shaped, this is one donut and there's another donut shaped electron clouds. One is above the plane and the another is below the plane of the molecule or the ring. So the 6 p orbitals which are present on each of these carbon atoms, which is unhybridized, which is not participating in the hybridization. So each of one of these p orbitals has a single electron each. So all of them are having 1 electron each, so they can form a ring. They can overlap. All the p orbitals can overlap and form continuous donut-shaped electron clouds here. One is above the ring and one is below the ring. Okay. So this is the orbital structure of benzene here, and here all the p orbitals here form a molecular orbital covering all the 6 carbon atoms. So it can be more explained in terms of this molecular orbital, HMO, Huckel's molecular orbital theory. So let's look at that in our next video. Yes, if you like my video, please do like, share and subscribe my channel. The whole chapter of this aromatic hydrocarbons from BSc first year has been discussed on my YouTube channel, and the link of it has been given in the description box.